Most people attack this problem with simulation. Flip k indices. Repeat. Track the string. And it works for small inputs, but the constraint goes up to 100,000. This isn't a simulation problem. It's a parity invariant trap. And if you miss that, you'll either TLE or confidently return the wrong answer. Today, we're breaking this down the way top 1% candidates think. Let's go. We're given a binary string, an integer, k, operation, choose exactly k, different indices, and flip them. Goal, make the entire string equal to 1. Return minimum operations, or -1, if impossible. Now pause. The keyword here is exactly k indices, not at most, not any subset size, exactly k. That single word changes everything. Let's decode the constraints. Is less than or equal to 100,000. We can't simulate flipping combinations. We need mathematical reasoning. Let's define z, the number of zeros, the number of ones, because ultimately only zeros matter. We need every zero to become 1. Example, s equals 0, 1, 0, 1, k equals 3 zeros, 2. Length, 4. We flip 3 indices per operation. Notice something subtle. Every operation flips exactly 3 bits, so total flips after t operations, t times k. But flipping twice cancels out. So what actually matters is parity, the parity of flips per index. If an index is flipped an odd number of times, toggles. If it's flipped an even number of times, it stays the same. That's the core invariant. Let that sink in. This problem is about controlling flip parity across indices. Let's try brute force. Naively, try all combinations. Breadth first search on states. Track visited strings. State space size? Todo the power often. For n equals 100,000? Impossible. Even greedy simulation per 0 won't work. Because flipping one index affects others. This is not local. It's global. So we optimize our thinking. We shift perspective. Instead of simulating strings, we reason about total flips. T times k. Distribution of flips. Parity constraints. Key insight. Parity invariant. Let's focus on the zero count. Call its. To make the string all ones, each zero must be flipped an odd number of times. That means the total number of flips contributing odd parity must match the parity of z. But total flips after t operations is t times k. So we need t times k mod 2 equals z mod 2. If that condition fails, impossible. That's your first filter. Key insight 2. Even k case. If k is even, each operation flips an even number of bits. So the total parity of the zero count never changes. If z is odd, impossible. Instant -1. No simulation needed. That's interview-level thinking. Key insight 3. Distribution limits. Each index can be flipped at most t times. But parity constraints limit effective flips. We compute the feasible range of flips assignable to 0 positions. This becomes a range feasibility problem, not a string problem, and that's elite reframing. Let's break down the solution. We start by computing n, the length of the string, and z, the number of zeros. If there are no zeros, we're already done. Return 0. Next special case. If k equals n, every operation flips the entire string. So we can only succeed in one move if every character is 0. Otherwise, impossible. Now the first invariant check. If k is even, each operation flips an even number of bits. So the parity of the zero count never changes. If z is odd in that case, immediate -1. From here on, we search for the minimum number of operations, call it t. Each t produces total flips equal to t times k. Now comes the core feasibility check. Inside feasible, t We verify 3 constraints. First, parity condition. Total flips mod 2 must equal z mod 2. If parity fails, stop immediately. Second, per index limits. An index can be flipped at most t times. But depending on whether t is even or odd, the maximum odd or even flips differs. We compute odd_max and even_max accordingly. Third, distribution feasibility. We must assign total flips across 0 and 1 positions. 0 positions must receive an odd number of flips. 1 positions must receive an even number. This creates a range. L, the minimum flips assignable to zeros. R, the maximum flips assignable to zeros. If L exceeds R, distribution is impossible. Finally, we adjust L to match parity. If a valid value exists within the range, T works. Now how do we search for T? We start from the lower bound, ceiling of Z divided by K. Then we iterate upward within a safe bound. If K is odd, T must match the parity of Z, so we step by 2. If K is even, we check every T. The first feasible T is the answer. If none work within bounds, return -1. No simulation.no state exploration. Only invariance and range feasibility. That's top 1% problem solving. Z equals s.count, 0. We reduce the problem to counting zeros. Never manipulate the string directly. Parity check. If K is even and Z is odd, return -1. If K is even, parity is locked. This is a pure invariant check. Interview gold. Feasible, T. This function asks, if we perform T operations, can we distribute flips so each 0 flips odd times? It ensures global parity condition. Each index flip limit. Range feasibility. Matching parity of 0 flips. This is constructive math validation. Lower bound. T equals ceiling of Z divided by K. Minimum operations needed to at least touch all zeros. Y upper bound equals 2n plus 5. We need a safe search window. Worst case parity adjustments can push T upward. This guarantees termination. Complexity analysis. Time complexity. Worst case, O(n). Why? Counting zeros takes O(n). Searching T up to roughly 2n. Each feasibility check is O1. Space complexity, O1. Pure mathematical reasoning. No extra arrays. Pause here. Notice what just happened. We never flipped a single character. We solved a string problem without touching the string. That's pattern evolution. Comment below. Did you first think simulation? Be honest. Why does an interviewer ask this? They're testing your ability to recognize invariants, your parity reasoning, constructive feasibility, and avoiding the brute force temptation. Common follow-ups. What if we flip at most K? What if K changes each operation? What if we want all zeros instead? How to present confidently. Step 1. Start with the parity invariant. Step 2. Show the even K trap. Step 3. Derive the lower bound on operations. Step 4. Explain the feasibility distribution. Defend your solution with math, not intuition. Think of it like distributing network load in fixed batch sizes. Each server, that is, each index, has flip capacity. Total workload is fixed. Parity constraint is the protocol constraint. We're solving constrained resource allocation. The core idea wasn't flipping bits. It was recognizing that parity is invariant, total flips matter, and distribution feasibility defines possibility. That shift from simulation to invariance is what separates average candidates from elite ones. If this clicked for you, you're not just solving problems. You're upgrading how you think. And that's what gets you hired. See you in the next breakdown.